This is going to be a collaborative presentation in the spirit of FLUIDOS, where we share resources and capabilities of various sites. I will start the presentation here with my colleagues Liubov, Nedoshivina, and Killian, Levacher. My name is Stefano Braghin. I'm a research engineer in IBM Research Ireland, and
I'm Liubov Nedoshivina. I am also working here with Stefano and Killian as a research engineer.
Killian Levacher, I'm an AI scientist in the same lab as IBM Research Dublin.
And we're going to present the paper AI-driven workload management in MetaOS, which is a work that we performed within the lab within the scope of FLUIDOS. And basically, the work is about pushing workload management orchestration in a dynamic cloud environment to the next level. This work has been presented at MECC, a workshop organized by in part by member of FLUIDOS, as a way to basically discuss and collaborate on meta orchestration on MetaOS within cloud environment. The reason for this work is that traditionally orchestration of workload focuses on large jobs executed within in a high performance environment, which basically means that we have jobs of known size and known resource requirements to be scheduled and organized within large infrastructures, so that the utilization of the resources is maximized, or it's maximized the throughput of applications that are being executed. The system that the scenario that we are targeting is slightly different, in the sense that we want to target to tackle the problem of organizing and orchestrating the execution of workloads of unknown size, or those sizes can change along the time of execution, so that it's not possible to perform a schedule a priori or reschedule the same application. Also because in a lot of cases, these type of applications, say jobs that are run periodically, or microservices that are executing, for example, in a microservice architecture, vary in size, and every time we have a new deployment, it's actually a new version of the application that is being deployed, which means that we cannot leverage, we cannot perform a static allocation of the job within the infrastructure. Moreover, we want to go beyond the requirements, the traditional requirements that are just availability of certain computation capabilities, or memory, or accessibility, the ability to access certain datasets. In particular, we want to allow the user to express what we call intent, so the high-level requirements, that service level requirements that they want the application to perform against in a more expressive manner, so that they don't need to specify, for example, how much CPU, but they can specify the throughput that they want to see within their application. Moreover, we want to go beyond that, as I said, and allow the users to specify more types of intents. For example, to have performance-oriented intents, like the throughput I mentioned before, or for the application to have a certain latency against a given set of services, for example, or they wanted to be able to specify the request, the requirement of a service to be connected to the application. Or what they might want is also to guarantee that the application is running in given infrastructure that is compliant with certain compliance standard. For example, it needs to run in a GDPR safe environment, or it needs to be executed on machines that are DORA compliant, for example, if we are in the banking environment. which basically means that we need to allow the user to express those intents. The meta orchestrator needs to be able to reason on top of these intents and also on top of on what the application is actually with respect to what is being deployed. So the Docker images that are involved. This means that we need to not only rely on traditional techniques, but we need to use artificial intelligence in order to basically bring this orchestrator to the next level. So just to have a more graphical representation of what I meant, we want the user to specify intents in a language as close to the user as possible, and also as familiar to the user as possible. These intents can then be specified, for example, in a Kubernetes manifest, because as FLUIDOS, we are operating with the assumption that the deployments or that the entire infrastructure is built on top of Kubernetes, which means that the developers are assumed to be familiar with Kubernetes, so they can specify Kubernetes manifest, and they can enrich this manifest with the intents, so with this type of request that they have. The system will read all this information and will use a model-driven approach to select which component is able to reason on top of this information and perform a deployment of the application based on all these requirements. And the idea is basically that we can then model this type of satisfaction of execution of the application as a recommendation. So the orchestrator can look and find a template of machine or collection of machines that are able to satisfy the requirements, both in terms of performance, compliance, and so on and so forth, and then deploy the application in one of those machines once this template has been instantiated either locally, so in local FLUIDOS nodes, or in other nodes that are accessible through the rest of the services that are provided by the FLUIDOS project, namely RIR. Of course, to do that, we need to be able to reason and train models, which is not easy, given the fact that a lot of these of the data sets that might be useful are not exactly publicly available because they contain information about the specificity of the infrastructure of the various organizations that are running this workload. But because of that, we work on expanding and leveraging the public information that is available, and also add some tricks to everything. Yeah.
Yeah, so Stefano was saying finding suitable data sets for this ML task has been one of the most challenging aspects of this work. There's no existing data set really that fits exactly our use case, and so this is still something we're working on as of now. But the main problem is that there's a lot of data sets that provide cluster traces, but none of them have any intent mapping between the intents and the cluster traces. And also in most cases, for privacy reasons, as Stefano was mentioning, traces don't have any details about the jobs that were run them. So our approach has been to try and find data that were as relevant as possible for this task, try augmenting them for use case specific data, merging them, and also trying to build our own data sets using various modeling scenarios. So at the moment, we've got like 3 categories of data sets we're using. So cluster traces, cluster modeling traces, and then standard non-cluster based data sets. So with respect to the cluster traces we're using the Google cluster traces, the GCT dataset. So that's a collection of traces that were run during about a month on 8 different board cells. And these provide us with attributes such as CPU, memory, and location of the jobs being run. The BitBrains dataset is a collection of traces from about 1,750 VMs that were used in the data centers from BitBrains. And they provide the same information as the GCT dataset, but also performance metrics with respect to whether they're using SAN or NAS devices. And then we also have the Materna dataset that we're using that's representing the traces of over 1,500 VMs. Again, same thing, it has the same attributes as BitBrains and GCT, but also has a disk write throughputs. And so we're also trying to create our own dataset, basically based on simulations of a cluster in which we will have complete data about the intents requested and the actual performance of the deployed jobs, specific intents with a feedback loop. Sorry. So this is something we're still working on, but we're hoping that would be the most accurate and reliable data set we could have for this task coming forward. And then we're using also non-cluster based data sets as baselines. This is just to validate our model architectures. So out of all of these data sets, we're also augmenting these data sets with various data such as location, also creating synthetic pod manifest that represents the jobs being run. And yeah, and this list will be growing very soon as well. So basically, we have a total of 5 data sets that we're using for these experiments, plus various versions of each, including combinations of these data sets and also augmented versions of each. And regarding models, we're currently working on different approaches, different architectures, and including some baselines. But basically, maybe next slide. I don't know who's, yeah. So because of these reasons, because we have like these various data sets and various models we're trying to train on, we wanted to try and build a training pipeline that would help us switch any data sets easily, and also any models being trained, both to streamline the development of these models, but also for evaluative comparative purposes across models and across data sets. So yeah, so because each data set basically comes in its own format and data, so we had to build a pipeline to standardize both the model data inputs across these various data sets, and also the way models were trained and evaluated. So you can see, so basically you can see the pipeline we built more as a kind of universal data set augmentation, injection, model training pipeline. And the way it works, basically, we start with data sets that each come in their own formats. We convert these data sets into a common formatting. Then we process this data set to make it model ingestible. We augment the data set in this form, and then after that, basically, we are training various models, building, training, evaluating them, and then servicing them to that model pipeline, and then creating an ensemble of an orchestrated ensemble of all of these models. Yeah.
So from the data to the method itself, as we mentioned, we are into model-based workload management, and from the data sets, any data set, we extract intent parameters, and also we extract some contextual knowledge from the previous deployments or some additional information from the intent. And then we run a baseline orchestrator, which is in a nutshell just a brute force approach that loops over the list of all available resources, and it compares the intent requests with the parameters of the machine, and it selects the first acceptable satisfactory resource configuration found, so close to random choice. And then we propose 2 model-based orchestrators, candidate generation or CG, and 2 towers. And next we consider both of them in more details. Candidate generation. As you can see, it is a very simple model, fully connected model architecture with 3 layers. In a nutshell, it implements machine learning version of matrix factorization, a very common approach to solve recommendation problem. But the trick here is in the input, because this model leverages embeddings, and these embeddings are basically the translation of the pod manifest with all intents injected into the embedding space, into the vector form. Also, we use as an additional input previous deployment history, like was similar or same pod manifest successfully deployed on this certain machine, or there are some problems, so we can use this information to guide the model. The model is using softmax regression to select the best machine for a given input, and well, it is really simple, and it was our first choice just to validate the data sets and to see if a problem can be solved by this approach. The next method is the two towers model. It is way more advanced model, which consists of two separate stages, which are then trained simultaneously. And stage one, or tower one, is a retrieval model that selects from all the initial subset of candidate machines. It selects top n, which are like the best candidates for a given input. This is important, especially for the cases where we have large cluster or large set of clusters with thousands of the machines, and this allows to narrow down the list of potential candidates. And the second stage is a ranking model. It ranks each candidate. That also helps the model to guide the process. It basically ranks the input set of configurations according to the input, according to the intent input. And it also leverages the same embeddings as the candidate generation model. We still translate the information from the port, but we also specify explicitly the resources needed, for example, CPU or memory requirements, for the ranking purposes, because this way we can simplify this process. As I mentioned before, both towers of the model are trained simultaneously, and then the model predicts the machine ID, the configuration ID that would suit the desired requests. And as for the experiments, from the datasets that Killian mentioned, we selected two the most comprehensive. These are GCT and BigBrains. And we introduced two metrics to measure how well model performs in this maybe not that trivial setting. The first one is the percentage decrease that shows how well model performs in terms of resource allocation in comparison to the baseline. So how less resources will be consumed if we will follow the model recommendation. And the second metric we introduced because the first one, it doesn't capture all the intents, potential intents, for example, location. We cannot measure the decrease of location, for example. And this metric we call intent request satisfaction. It measures number of satisfied intents. So for example, if the location from the pod was satisfied, so we found the perfect cluster. And using these two metrics, we try to evaluate our models. So here are the results. As you can see, the candidate generation model, it outperforms baseline allocation significantly, at least in terms of resources allocation. Well, we were able to achieve like up to 70% or even 93% less resources allocated with recommendations of this model. And also about the intent satisfaction level, well, it is not like ideal, not 100%, but still close to it, which is surprisingly good for this simple model. And about the two-tower model, I will pass the ball to Killian, who explains a bit more in details the results.
Yeah, so the two-tower architecture basically overfitted in these experiments, and I think that was the first attempt to create a standardized, like two-tower models is usually a standard approach for model architectures for recommended systems. So we went for this as soon as we realized this was a recommendation task. But yeah, the data set that was way too sparse for this kind of architecture. It was an overkill basically for that task at the time. So yeah, we suspect that's why it's overfitting. But now that we're building a more comprehensive data set, we're hoping to be able to reuse this and see how it performs with the new versions of data sets.
Now, everything looks great on from the result point of view and from the fact that the system is taking into consideration the intents that are specified by the user. But a question that might rise is, does it really exist or it's only on paper? And the answer is that it exists. The model-based method orchestrator is available to be used and tested, and please use it and test it. We need feedback. It's available as an operator for Kubernetes, and we basically wrap requests from the user in a custom resource called FLUIDOS deployment that helps the method orchestrator to track the state of the deployment within the entire continuum, and allows us to reason and perform our recommendation on the deployment itself. The user doesn't need to interact directly with the orchestrator, so they don't need to create a manifest of type of work of kind FLUIDOS deployment, but they can just use their standard deployment and leverage the Kubernetes plugin that was developed still again as part of the FLUIDOS project. In this context, the user simply needs to call kubectl FLUIDOS as they would do for kubectl apply, and the system automatically will wrap the request if it's of the FLUIDOS of the Kubernetes manifest, and invoke the appropriate application on the cluster. Behind the scenes and a bit more in details, the client, so the kubectl plugin, will actually select the path of scheduling of the job based on how the job is defined, and based on the existence or not of intents specified by the user. If the plugin receives a traditional Kubernetes manifest with no intents specified, it will assume that the user just wants to deploy a standard, a traditional Kubernetes manifest in their local infrastructure, and it will just forward everything to the native Kubernetes services. On the other hand, if this job is defined using the MSDL language, it will invoke the appropriate services as described by other partners of the FLUIDOS project. But if the manifest is of type Kubernetes and contains at least one intent specified, it will then go through the pipeline that we described before, where our operator will basically analyze the manifest, extract the intents, enrich them with additional contextual information and any type of information that they can either obtain from the user or that are specified within the system configuration. Select from the collection of models that are available, for example, the candidate generation and 2-tower that have been presented before, and then use one of them or an ensemble of these models as a way to create a recommendation of where the job should run. It will then interact transparently from a user point of view with the REAR protocol that has been designed within FLUIDOS to allow the advertisement and discovery and acquisition of resources in order to decide if a job needs to be executed locally or remotely through the expansion of the continuum. Note that this expansion is dynamic in the sense that if there are new resources, or if a job finishes and if the continuum is not required anymore, it will be automatically removed. Also will be when we will support that feature. At the moment, we only expand. But that's the point of having this operator, basically managing the expansion and contraction of the available resource, of the resources available locally. Next slide, please. As I said, all of this is available. It's publicly available and open source. It's been released in the FLUIDOS project GitHub organization. Feedbacks, as I said, are more than welcome, and we are actually looking forward to a lot of issues because this is a research project and the code is it's not yet production ready. So please use it so that we can improve it. Thank you.